So welcome to Unit 6, the second half of calculus, the beginning. First half of calculus was the derivative. We spent a long time with that. We're going to spend a long time with this idea. We start off with something called integration. We will learn lots about that. The accumulation of change, I hope you already have a really good idea about because we just did that with the Desmos activity. Velocity is the change in position. And if we add up all those changes, we found out how far we went. So that's an accumulation. Accumulation means adding up all of those small amounts of change. And from our quick look at the discussion, some of us were already thinking about this. We're going to have really weird stuff. So how do we get that really weird stuff to work out area-wise? Because area was the big connection. If we found the area formed by the horizontal axis and the curve and whatever the bounds were on the left and the right, we figured out what the distance traveled was. And you may have noticed that a lot of those curves that you studied, especially in the challenge section, it was kind of hard to do that area. Kind of hard to the point of impossible. And you just found yourself kind of like saying, that's pretty close. Well, that's the approximation idea. So we'll begin to understand how we actually do this using the approximation technique. So that's what we'll be studying. But first, and with that idea of approximation in mind and the stuff we already did with Desmos, what I want you to do is take a few minutes here and come up with the area of the shape. The shape is bounded on the top by the graph y equals 16 minus x squared, and on the bottom by the x-axis. So take a couple of minutes, think about your area. This then is the graph of the shape we're talking about. So we have our function 16 minus x squared. It has x-intercepts at positive 4 and negative 4, comma 0. A y-intercept at 0, comma 16. You may be curious about why I chose those points to mark and no other points. Well, that's because, did you know there is an area formula to calculate the area of this shape? So this shape right here, this shaded region, if you will, using old school shading. That right there has a formula. It's actually been around for thousands of years. I believe it was first written down, from what we can tell, in Euclid's Elements. So there is an area formula for it. It's 2/3 base times height. I don't expect you to memorize that formula. I don't care if you think about the formula after this moment in time, but just know that that formula finds the exact area of that shape. So the base is horizontally along the x-axis from -4 to 4, 8 units. The height is the y-axis up to 16. So if we do 2/3 times 8 times 16, we know that the area is 256 thirds, or 85 1/3, 85.333, rounding correctly. Again, before we move on, I don't care, and you shouldn't care about that formula. We're just using that because it's going to help us guide our future discussion here. So most of you probably were doing something like this. So you may have done something more creative, but you probably tried stuff like this. So in this first one here, I just drew a rectangle that went along the x-axis and then went up to the y-axis, and I said, that's my area. Now I looked at that and I said, well, I know that's not going to be the area, right? It's going to have all this extra stuff. It's going to have that extra stuff there. So it's definitely going to be too large. And we know if you believe me that this formula is correct, of course, that 8 times 16 is definitely going to be too big. Some of you might have just done a rectangle inside. So I did it from -3 to 3, and that's going to be 6 units. And then to get the height here, I did 16 minus 9. Why 16 minus 9, you say? Well, because this point is on the curve. And to get the coordinates of that point, I substitute 3 in. F of 3 is 7. Okay. Some of you might have gone crazy, and you might have gone with a triangle, 1/2 base of 8, height of 16. Okay, we know that's not going to be right because we got these gaps again. So this rectangle has got some overages. This rectangle has got some gaps. This triangle's got some gaps. But this triangle idea actually takes us in a way. So there is a proof for the value of pi done again thousands of years ago, which is miraculously done without limits. But the idea is you can get an upper bound for the area of a circle by circumscribing a rectangle and then a shape with more sides. So this has 1, 2, 3, 4, and this has 1, 2, 3, 4, 5. And you get a more and more accurate picture because notice how these gaps are getting smaller each time. So that's for, that's for inscribing. So that's going to be a lower limit for the value of the area of the shape. And then if you circumscribe, so you go around, you get an upper limit. So what you can do is do more and more sides, so you get a more and more accurate idea. So this is where the earliest proofs for the value of pi came from. So this idea, we're on to something with it. Okay, so we're going to do some more and run with that. But we are not going to use more sided shapes because that's a really hard calculation to do. Instead, we're going to keep things basic. And instead of doing more sided shapes, we're going to use one of the easiest shapes to find the area of, which is a rectangle. Think you would agree finding the area of a rectangle? Pretty easy, base times height. Okay. And we're going to draw the bases any way we want, but for efficiency reasons, we're going to use a uniform base. So uniform meaning the same or identical or equal. Okay. So what we're going to do is we're going to take this idea here for that first and second estimation that I did, and we're going to draw more rectangles. So instead of doing one rectangle, we're going to do several rectangles. So think about what would happen if instead of one, I did 2, or 3, or 4, or 5, or 6, or 7. We're going to have the same kind of situation as we do when we do a shape with more sides. We're going to have smaller overages and smaller gaps. So we're going to be more accurate. And those bases, those are always going to be along the x-axis. So that's the base. But what are we going to do with the heights? Well, the heights, like I mentioned already, for that second approximation scheme I gave you, I went to x equals 3, and then I found the point at 3, which I did by doing 16 minus 9 to get 7. So once we're able to do the bases, we can get the heights by substituting those x values in to the function. And then to give you a big picture idea of where we're taking this, we're going to do this 3 ways. Well, that's not true. You have the option of doing it 3 ways. How do you know which way is better? Well, depends. But More on that later. So what I want you to think about, and we're going to be redrawing that original picture several times, is 4 rectangles of uniform base. So what's going to happen here if you look at this picture? If we do 4 rectangles of uniform base. So uniform or equal means I'm going from here to here, so 8 total units, and I need to do 4 rectangles. So in order to fit that in, each one of these is going to be 2, right? It's going to go from -4 to -2, that's 1. -2 to 0, that's 2. 0 to 2, that's 3. 2 to 4, that's 4. So each of these has the same base of 2 units. And then, depending on how I draw my rectangle, more on that in the future, I'm going to know how to draw my height to calculate the area of the rectangle. So, to recap, if we're doing 4 rectangles of uniform base, I went through it quickly. How long was the base? Base was 2 units. We refer to this when we talk more about the method. Don't look at this picture over here yet. This is setting up subintervals from -4 to 4. So what do I mean by subintervals from -4 to 4? I mean, we're talking about going from -4 to -2. That's one rectangle. And then from -2 to 0, that's our second one. And then from 0 to 2, that's our third one. And then 2 to 4, that's our fourth rectangle. So each of our 4 rectangles has a uniform base of 2 units. We start at -4, and if we go 2 units, we go to -2. If we go 2 more units, we go to 0. 2 more units, we go to 2. 2 more units, we go to 4. So what I'm just trying to share with you is how we're doing these repeated rectangles, because we can do them however we want. Like if we want to do one great big fat rectangle like this, and then do 3 little rectangles here, we could do that too. But for our purposes, we're going to keep those bases the same. And for those of you that have been studying programming, you'd be like, oh, a uniform base is great. That's much easier to program. Yes, yes, it is. Okay. And then the height is going to be a point on the curve. So what do I mean by a point on the curve? Well, take a look at my picture that is super hard to follow. Don't worry, we'll be breaking this down again later. So there are 3 common techniques for drawing the rectangles when we're doing a uniform base or a not uniform base. And the L stands for left, the R stands for right, and the M stands for midpoint. So what we're doing to start is we've got our shape here, right? It's the shape formed by the curve and the x-axis, which is sometimes referred to as the area under the curve. I don't like that very much, so I usually say the area between the curve and the x-axis, but they are used interchangeably and correctly. So again, our first rectangle goes from -4 to -2, the second one from -2 to 0, the third one from 0 to 2, the last one from 2 to 4. We can choose to use the x value at the left side for our 4 rectangles, or the right side for our 4 rectangles, or we choose the midpoint between the left side and the right side. So what do I mean by that? If we're doing left-sided rectangles, our rectangles' heights are going to happen at -4, -2, 0, x equals 2, and then that's our 4 rectangles, right? First one, -4 to -2, the height is at -4. Second one, -2 to 0, the height is at -2. Third one, 0 to 2, the height is at 0. Fourth one, 2 to 4, the height is at 2. Those would be the left values for the 4 rectangles. So that's one option that's commonly done. The second option that's commonly done is the right rectangles. So what do I mean by that? Well, this one's a little bit harder to see, but it's still the same shape. And you'll notice that from -4 to -2, my rectangle height this time is over here at -2. And then from -2 to 0, the right side of -2 to 0 is up here at 0. And then the third rectangle from 0 to 2, the height is at 2. And the fourth rectangle from 2 to 4, the height is at 4. And here then is the last. The last one is the midpoint. And we call it the midpoint because it's the midpoint of the x values, or the midpoint of the subinterval. What do I mean by that? Well, remember the first rectangle has a base that goes from -4 to -2. We draw the height at -3. -3 is the midpoint between -4 and -2, right? If you go from -4 to -2, add those together, you get -6, divide by 2, you get -3. Or you could think of it as -4 to -2 is 2 units. Half of that is 1 unit, -4, 1 unit to -3 is 1. Okay, for the next subinterval, we're going from -2 to 0, and we draw the height of our rectangle at -1. Where does -1 come from? -1 is the midpoint between -2 and 0. Again, a couple ways you can think about it. One way, you can say -2 plus 0 is -2, divided by 2 is -1. Another way, you could say -2 to 0 is 2 units. I want to go halfway, which is 1 unit. -2 to -1 is 1 unit. Repeating this again twice more nets us midpoints for 0 to 2 of 1 and 2 to 4 of 3. So you may be wondering, why do we have 3 different ways? Why not 5 ways? Why not 10 ways? Why not 11 ways? And the short answer is because these 3 ways pretty much do exactly what we want when it comes to the idea of approximating. We get from these 3 things an over approximation, which is when you've got areas outside of the shape, you've got those overages, extra area. We get an under approximation, and these are areas inside of the shape. So what we've created is the situation where we can say the area is this small and the area is this big. So the area is somewhere in between those. And then we've got our third option, which is going to be more accurate. We're, I think, going to get to this today, but we may not. And there's an even more accurate representation than these that are typically used, but it doesn't quite fit in with what we're doing. And it's a trapezoid, a trapezoidal method. I just tried to spell the word method as math, method. Here I am making up words. Okay. And the reason why I divide these like so is because these first three are attributed to a mathematician named Riemann. And because we're adding up a bunch of rectangles, these are called Riemann sums. So the Riemann sums comes in 3 flavors. This is not Baskin-Robbins. P.S. Baskin-Robbins is not 31 flavors. Tried to get some the other day, and they were minus like 6 flavors. So the people behind us in line at the drive-thru are probably cranky, but when you give somebody your first 3 options and they're like, we don't have any of those, like, what are you supposed to do? So there's 3 flavors for Riemann sums. They are a left height, where we use the leftmost x values. They are the right height, not right isn't correct, where we use the rightmost x values. And then generally in between these is the midpoint. And the midpoint again is the midpoint between the x values. So you could think of this a little bit like Goldilocks. Too big, too small, just right. And then we've got the 4th option, which is why math is better than English. We have the trapezoidal method, which is even more accurate than the midpoint. So let's start doing the part that a lot of you get excited about. Like when you're like, oh, I'm doing math, you want to push some numbers around the paper. Okay, well, let's push some numbers around the paper. Okay, so we'll start off with the right. Okay, so same shape. All of our rectangles are here on the x-axis. So what I've done is I've broken out the x-axis. So that first rectangle has a base that goes from -4 to -2. So that's the base right there. So where is the height of the rectangle going to be? The height of the rectangle, because we're doing right, is going to be at -2. So my rectangle goes up to this point right here. And that's the first area I would find. So this point right here is, let's see, 16 minus 4, that's 12. Pretty sure I did that right. Okay. The second rectangle goes from -2 to 0. And then because we're doing a right height rectangle, we would go from -2 to 0. The right side is 0. So we'd put our point right there. That is the second rectangle whose area we're finding. Okay. Then the third rectangle goes from 0 to 2. We're doing the right. So we've got that. And then the last one is going from 2 to 4. So we've got this really awkward rectangle. I just realized I forgot to put in the other function values, excuse me. It's not much of a rectangle, that last one, is it? That fourth rectangle. Okay. So what do we got? Well, for rectangle 1, we have a base of 2 times a height of 12. For rectangle 2, we have a base of 2 times a height of 16. For rectangle 3, we have a base of 2 times a height of 12. And then for rectangle 4, we have a base of 2 times a height of 0. So 24, 32, 24, and 0. Add those together. 48 plus 32 is 80. I think. Sure, 80. Okay. Left. Going to be the exact same thing we just did, but instead of choosing -2, 0, 2, and 4 for those heights, we're going to be choosing from -4 to -2, the left, which is -4, -2 to 0, the left, which is -2, 0 to 2, the left, which is 0, 2 to 4, the left, which is 2. So -4 is here, -2 is here, 0 is right there, 2 is there, 4 is there. So again, the base of the rectangle, that's along the horizontal axis, the x-axis in this case. And I draw my height at f of -4. So not much of a height. Second rectangle goes from -2 to 0. That's the base. The height, we're going to do the left side at -2. So that's right here, f of -2. So that's the rectangle right there. Third rectangle, 0 to 2. Left height is 0. So that's this height right here. So there's my base. My height's right there. This should be perfectly symmetric, but you know I'm deficient in that category. And then the last one, 2 to 4, we're going to go height at 2. So base is from -2, I'm sorry, 2 to 4. Looks like that. So our first rectangle, base is 2, height is 0. Second rectangle, base is 2, height is 16 minus 4, that's 12. Third rectangle, base is 2, height is 16. Fourth rectangle, base is 2, height is 12. Oddly enough, it's the same. Huh. Last one, we're going to do midpoint. Same x value for the intervals, different x values that we're doing though, because we're doing the midpoint. So -4 to -3, the midpoint is -2, the midpoint is -3. -2 to 0, the midpoint is -1. 0 to 2, the midpoint of 1. 2 to 4, the midpoint is 3. So if I've got -4, -2, 0, 2, and 4 on here, we're going to be doing the midpoints at -3. That's my first height. At -1, that's my second height. +1, that's my third height. positive 3, that's my fourth height. The rectangles look like that. Okay. All of these have a base of 2. We have different heights this time. Negative 3, f of negative 3, 16 minus 9, that's 7. F of negative 1, that's 15. F of 1 is also 15. F of positive 2 is 7 again. So that's 14, 30, 30, and 14. So 44 and 44 is 88. Interesting. So here's what I want you thinking about. I want you thinking about kind of those ideas I talked about at the beginning, where we have over and under, can't really see that, sorry, approximations. What do you think about that? And the best answer I have for you is going to be to study the geometry. Hopefully you enjoyed your nice long break. Quick recapitulation. We looked at 3 different styles of rectangles, looking at the same interval from negative 4 to positive 4. We said that we're going to do a uniform base of 2 units. So that meant that the first rectangle was going from negative 4 to negative 2, the second rectangle from negative 2 to 0, the third rectangle from 0 to 2, and the fourth rectangle from 2 to 4. So what we mix up each time is where we're drawing the heights. So pictured here is if we do right heights. So what I mean by that is from negative 4 to negative 2, the rightmost value is negative 2. From negative 2 to 0, the rightmost value is 0. From 0 to 2, the rightmost value is 2, and from 2 to 4, the rightmost value is 4. And then those 4 rectangles are drawn that way. Then if we do left, we choose negative 4, negative 2, 0, and 2. And if we do midpoint, we have to calculate the midpoint between each of the values, negative 4, negative 2, negative 2, 0, 0, 2, and 2, 4. All of those go into the function because all of the rectangles go from the x-axis up to some point on the function. So that's where all these values came from. While you were away, I did an additional set of calculations. I do not want you to write down these additional set of calculations. Instead, I just want you to observe that when we go from 4 rectangles to 8 rectangles, we get a more accurate value. What do I mean by that? Well, the exact value we said was 85 1/3. The first time around, we had 80s and 88. 88 is there. The second time around with 8 rectangles, I got 86 and 84s, which are closer than the original. Agreed? Yes. So if we were to continue this and do more rectangles like 9 or 10 or 12 or 16 or 25 or 80 or 100 or 1,000 or 10,000, or if it were possible to do infinitely many rectangles, what's going to happen with the area approximation each time? We would notice each time we're going to get closer and closer. And that is the big conceptual takeaway. So again, I don't want you to copy down all these calculations. All those calculations are like 7th grade math and we're doing calculus. Instead, what I want you to take away here is the idea that more rectangles is more accurate. Okay. Next big takeaway we've already discussed. We're using uniform base. That is to expedite the calculation process, but you don't have to. You could do any base. And then the third thing is, and you may have noticed it in the writing I did do, so what you can do is this. You can factor out that value and then add up some heights. So there is some practice on WebAssign to go with these ideas. I know that the calculations are time consuming, so they're going to feel very important to you, but I don't want you to focus on the calculations. The calculations are the smallest part of what we are studying. Okay. One last piece of math to review before we go on to the next thing on our list is sigma notation. Okay. This dude right here is a capital sigma. Lowercase sigma is used a lot in statistics. Capital sigma is here. And it's translated as sum of. Not sum of as in choose a few, sum of as in add everything. So your 30-second review of sigma notation is right here, and this is the notation. You have a counter at the bottom. You have a counter on the top. The bottom is the starting counter. The ending is the top counter. You take the value, put it into whatever formula is over here, do that calculation, then increase your counter by 1, it's always a whole number, until you reach the final value. And you plug those in to this formula, add up each individual value, and call it a day. Now your graphing calculator will also do sigma notation. Nope, it's not that one. Is it on here? Yeah. So it's under math summation. So if I want to go from x equals -4 to x equals 10, and I just want to do it for x plus 4, what my calculator is going to do, well, it's not actually what it's going to do. There's a shortcut formula here. But what my calculator does is it substitutes in -4, gets 0, substitutes in -3, gets 1, -2 gets 2, -1 gets 3, 0 gets 4, 1 gets 5, etc., all the way up until it reaches 10. And then those values get added up to equal 105. So go ahead and use your calculator for that. This is notation we will be taking advantage of in a calculus sense. I want you to arrive at some level of understanding for that. All right.